All right, so we're going to do another example of an acid. We did 10 to the minus, what was it, 10 to the minus 8 molar HCl? Was that the last one, the calculation that we did?
Then we had to do the quadratic.
Yeah, and then there was significant contribution of hydronium from. Did we do the solution inventory for that?
Yeah,
Yeah, okay, good. And the pH. And so the next example we're going to look at is going to be another acid, except rather than a strong acid, this time we're going to do a weak acid, and it's going to be 1 times 10, or actually, let me go more digits this time.
Chapter 17.
Yeah, this is just chapter 17 continue. I'm behind schedule. That's all right. So we're going to look at 1.00 times 10 to the minus 7 molar HCN. The first thing that you should notice is this concentration. That concentration is extremely small. And so it's extremely small, and the more dilute a solution is, the more it resembles pure water. Although, would you want to drink this? Like, I'd drink the 10 to the minus 8 molar HCl, no problem, but I wouldn't drink the HCN.
Probably wouldn't drink anything with cyanide.
Yeah, don't drink anything with cyanide. HCN is an acid, but in pure form, it's a gas, hydrogen cyanide gas. This is hydrocyanic acid in the aqueous form. Hydrogen cyanide gas is what they used in the gas chamber at San Quentin. Except they made it. You know how they made it? They took a cyanide salt and then added acid to it. So if you take like sodium cyanide and add acid, you're going to make HCN gas. And so they can make it on demand. But it's quite toxic. Did I talk about this already or not? So we aren't going to be working with any hydrocyanic acid. But this just serves as an example because the K is kind of small on this. The Ka for this is 6.0 times 10 to the minus 10. And so it tells you it's a pretty weak acid. You know, strong acids would have a Ka that's very large. This Ka is quite small.
So quick refresher, is Ka kind of resemble Kp and Kc in that a larger value implies that the whatever the reactant prefer the product side?
Mm-hmm.
Okay.
Yeah, but we have to know what the reaction is. The A stands for acid plus water or acid hydrolysis. And so this K is for what reaction? The reaction, whenever we have a Ka, it's acid plus water. Water is going to be our base. And so if it's acid plus water, what we're going to do is we're going to form cyanide and hydronium. I'm going to flip the order. I'm going to write it hydronium plus cyanide. And so this is our Ka equation. So the Ka expression would be the hydronium ion concentration raised to the first power times the cyanide concentration raised to the first power divided by the HCN concentration raised to the first power. And water is a pure liquid, and so its activity would be 1. Just stick it in. And so this is the Ka. So a small Ka value means it favors the reactants. A large Ka value favors the product. And so weak acids don't produce much hydronium because they have a small Ka value. But strong acids produce a lot of hydronium. And hydronium is going to alter the pH. You know, when we stick a pH meter in there, it's not measuring how many HCN molecules there are. It's measuring how much hydronium generated. And so we say that when we have an acid solution, our strategy is to look for hydronium ion producers. when we have bases, we don't look for hydronium ion producers. What do we look for bases? Hydroxide, yeah. So the most obvious hydronium ion producer here is HCN. And so we want to figure out how much hydronium ion is produced in this. And so we start off with 1.00 times 10 to the minus 7 molar. And we imagine that none of these molecules have collided with water, so that the initial hydronium and the initial cyanide are 0. So essentially what we do is reset this. In reality, this is already reacted, but what we're going to do mentally is just reset everything. And we can't start here because we don't even know what the equilibrium concentrations are. And so it just makes sense to reset this to the left. And that's what we do for all these problems. We just imagine nothing's happened yet. And then there's going to be a change. The change is going to be minus X molar, plus X molar, and then plus X molar here. And so at equilibrium, we're going to have 1.00 times 10 to the minus 7 minus X molar, and then X molar, and then X molar here. And so we can solve for X. We know that this is equal to 6.0 times 10 to the minus 10, and that's going to be X times X, which is X squared, divided by 1.00 times 10 to the minus 7 minus X.
Professor?
Yeah.
Can we have an acid that is in a solid form, as far as like the state of matter?
Mm-hmm.
So in that case, would the concentration just be 1, or how would we?
No, activity would be 1.
Activity would be
Yeah.
1, concentration would be something different.
Yeah, concentration would be something else. So let's say HCN were solid. We could have HCN solid here. There are different approaches that we could do to it. We could have HCN solid plus H2O gas, H2O liquid, and then that just gives these species here in the K equation. I think having a very small K like this, 10 to the minus 10, means that the change is small. In this case, this is with the given conditions. Would you want to reset this? Would I want to reset this to the right? No. I don't want to reset it to the right because the K value here is small, which says the reactants are favored. So this makes sense to leave it reset to the left. I could have reset it to the right. If I reset it to the right, then I'd just assume it all, ionized. And so I'd start off with 0, 10 to the minus 7, 10 to the minus 7 here. Could have done that. But it would make no sense to do that because this more closely resembles the equilibrium conditions. And we want it to more closely resemble the equilibrium conditions, at least the initial, because we want the change to be small. If the change is small, X, then it's likely that the simplifying assumption works. But there are two factors that make for a good simplifying assumption. One is the change should be small. The other is the initial should be large. You want if you add a drop of water to the ocean, right? The ocean's volume increased, but did it increase much? No. And when I look at this initial is quite small. So I start to worry, this doesn't seem like a big ocean to me. This seems like a small vial. If you add a drop to a small vial of water, it's going to change it more significantly, the volume. And so I worry, and therefore the book has this thing you could do. The book has a ratio you can calculate. The ratio is the initial over the K. If the initial over K value is 1,000 or greater, that is, the ratio of the initial divided by the change, if this will give this indication of the change is big, then it should work. But I don't bother doing that calculation because I don't want to debate, will it work or won't it work? Because how much time do you spend debating that? And that's lost time on exams, so I don't even bother doing that. What I do is I just try it. And so we'll just try the simplifying assumption here. And the simplifying assumption is that x is less than 10 to the minus 7, much less than 10 to the minus 7. And so that we're going to get x squared, and then 1 times 10 to the minus 7 minus x is just going to be 1.00 times 10 to the minus 7. And then we can solve for x, which is going to be 6 times 10 to the minus 17, square root of 6 times 10 to the minus 17. So we'll do that. 6 times 10 to the minus 17, and let's take the square root.
Is 6 times 10 to the minus 10?
Yeah, 6 times 10 to the minus 10 times 1 times 10 to the negative 7.
Gotcha.
And then I skipped a couple of steps, so that's why. And so I got 6 times 10 to the negative 17, and then we'll take the square root of that, and that should give me my x value. And my x value comes out 369. 7.74. I'm going to carry extra digits here. 7.7. I'm only allowed 2. 459. But I'm not going to carry. I think this is probably enough. Maybe one more. 7.74596 times 10 to the minus 369 times 10 to the minus 9. All right, now we have to justify our simplifying assumption by calculating the percent change. The percent change is going to be the change. In this case, the change is just x. It's not 2x or whatever. It's just x over the initial. And so I have this in my calculator. I'm just going to divide by 1 times 10 to the negative 7, 1 times 10 to the negative 7 times 100. And my percent change comes out to 7.74. So the essay fails. So I took a little bit of a gamble there. But it didn't cost that much extra time, versus if I calculated the ratio, and where's the cutoff for the ratio? It's a big grade. So I don't ever bother calculating the ratio unless I see the ratio is hugely small or hugely large. Then I might skip it. Skip the calculation if it's hugely small, or it depends on how you flip it. So fails. So that means we're going to have to use the quadratic. This is greater than 5%. So I need to get this into quadratic form. So let's go ahead and do that here. So I'm going to get x squared, let's see, plus 6.0 times 10 to the minus 10x minus 6.0 times 10 to the minus 17 is equal to 0. All right, so we'll go to the quadratic equation solver. And I'm just going to plug in the values here. So A is 1, B is 6 times 10 to the minus 10, so it's 6e to the minus 10. C is minus 6 times 10 to the minus 17, so I'll do minus 6e minus 17. Okay, and then calculate that. And so using the quadratic formula, we get an x, this, equals 7.45177 times 10 to the minus 9. Here we didn't make any assumptions. If we did the simplifying assumption, you can see we're off. Here it's 7.45, here it's 7.74. So it's off significantly. And you can tell this is going to be an error because of this large percent change. The larger the percent change, the bigger the error we expect in our x value. Although here we didn't make any assumptions. So the only error would be rounding error there. The quadratic is very common in chapters 16, or no, 15, 16, wait, 17, 18. 17 and 18 we do a lot of quadratics. So it could be worth getting the quadratic equation solver calculator, which is like a TI-36X or Casio FX115. It's worked pretty well.
Is there, do we have assignments for chapter 18?
Not yet.
Not yet, okay.
Yeah. I'll post the assignments for 18, probably over the weekend or something.
Yeah, no worries.
Okay. All right, so let's go ahead and calculate the equilibrium concentrations. And so I have this. I'm going to do 1 times 10 to the negative 7, 1 times 10 to the negative 7, minus 7.45, 177, times 10 to the negative 9. And I get 9.25 4823. I'm going to carry a ridiculous number of digits here. I'm not allowed this many digits again. 3, 6, 3, 6, 7, 8. Times 10 to the negative 8. Uh-huh.
Where did you get 6.0 times 10 to the negative 17?
I got that from this equation here. If you look on the black part. So I'm trying to solve this here, or get it into quadratic form. So I'm going to multiply both sides by this binomial here. And so 1 times 10 to the negative 7 times 6 times 10 to the negative 10 gives me 6 times 10 to the negative 17. And then minus x times this gives me minus 6 times 10 to the negative 10x. And then I get it all on one side. So I add 6 times 10 to the negative 10x and subtract 1 times 10 to the negative 7 from both sides. And then I get this formula in this form here. So that's where I got it. I just skipped a couple of steps in the algebra. Mm-hmm.
It also could work like if you're doing, I guess, the guess and check. If you just leave it like, or just leave it like the like how it is there with KA.
Yeah.
Equal to X squared.
Yeah. This works with guess and check too, so you don't have to buy the fancy calculator. And solving the quadratic is very time consuming. And so a lot of people find guess and check to be faster. But unfortunately, you can get unlucky with guess and check too. I mean, I think some people solved on the test. Some people solved a guess and check, and they had 3 pages of guess and checking. So, and they were here for quite some time, guessing and checking. And they came up to me and asked me, they asked me is something wrong because they just finished page 2 of guessing and checking. I don't know if you guys did guessing and checking, but this person did. So once you get good at it, it's faster than solving the quadratic. But the quadratic is, guessing and checking is going to suffer from rounding, errors and other stuff, and you aren't going to get as many digits. So for example, if I were guessing and checking, how many digits did I get for my x? I didn't write them all. I think 7.45177. That's a lot of digits to be guessing and checking, right?
I was gonna ask, is it like possible to guess and check when you have number in scientific notation?
Mm-hmm. Yeah. Yeah, you can do it this way, but if you're guessing, you usually start with one digit, then you move to 2, 3, 4. That's a lot of guessing to get this precise. But do you really need to get that precise? The only reason I'm getting this precise is not because it's necessary. It's because when I do my double check, I don't want rounding error to interfere with this. So the x values here, this is equal to 7.45177 times 10 to the minus 9. And this is the same, 7.45177 times 10 to the minus 9. The units for this are molarity here. There are no units in K, but we have to add the units when we go back to the ICE table. And so this is, I am manually adding the units here. The next thing is, the whole reason I'm carrying all these units is so when I double check my K value. So I'm going to plug these equilibrium concentrations back into my K expression here. And then calculate it. And so I don't want to write all those digits over again, so I'm just going to write the answer to it. So it's going to be 7.45177 times 10 to the minus 9 squared, divided by 9.254823 times 10 to the negative 8. And that gives me 5.99, how many nines do I have? 5 nines and a 3. 5 nines and a 3 times 10 to the negative 3, 6, 9, 10. And we compare it. So this is the K I got from these equilibrium concentrations compared to the K that was given, 6.0. So we're good. This would round to 6.0. But the question is this is an acid solution. Are there any other hydronium ion contributors? And the answer is yeah. So we're going to get this much hydronium, but are we going to get hydronium from, well, what other source of hydronium do we have in this acid solution? Water. And the question comes up, can we ignore the contribution for water? Is it like a drop in the ocean? Or will the contribution from water be significant? No, it would be a drop of water in, it would be like a drop of water in a dry lake, even though the drop of water would probably evaporate pretty quickly, but it would be significant. Like dry lake would be something like Lone Pine Lake. Well, anyway, what do you think? Well, when we think about water, the max that we're going to get from water is 10 to the minus 7. But if there's something called common ion, if we already have hydronium there to begin with, we don't have to go to the max. We can go much less than the max to get the Kw. And so normally water, in pure water, we have no common ion. And so let me talk about that right here. So normally when we look at Kw, it's H2O liquid plus H2O liquid. And this is going to produce hydronium. And what was the other product? Hydroxide. And so if this is pure water, we start off with 0, so we just reset this all to the left. And this is pure liquid, so if we add more liquid water, we don't keep track of it here in the ICE table. stoichiometrically, there is more additional water. So, in pure water, this is 10 to the minus 7, this is 10 to the minus 7. That's in pure water. But we reset it to 0 and 0. But there's a common ion here, and that common ion is hydronium. And this common ion means that there's hydronium here to begin with. If there's hydronium here to begin with, then we don't need as much additional hydronium from water to satisfy Kw. And so water is a liquid, so I'm going to completely ignore it, And then I'll start my initial here. And so what I'm going to do is I'm going to do this like this. The common ion from step 1 to step 2 is hydronium. So we don't start off with 0 hydronium. What we're going to do is we're going to start off with this much hydronium. That's going to be 7.45177 times 10 to the minus 9 molar. Now, step 1 had 0 hydroxide, so this is 0 molar hydroxide. So this is going to be the hydronium from step 1, or from HCN. So this is initial from HCN. Now the initial from water is normally 10 to the minus 7 and 10 to the minus 7, but what we're going to do is we're going to reset this to 0 molar and 0 molar. And so the easiest is to reset, because that just makes the algebra easier. So the total initial is going to be 7.45177 times 10 to the minus 9 molar primarily from the HCN. And then over here, both contribute 0 because we're resetting the water to 0. So all we did was reset the water, just form more liquid water, and then have it re-equilibrate this way. But when it re-equilibrates, the x is going to be a lot smaller, because x doesn't have to be as big. So when we look at the change for water, we're going to get plus x. This x is different than step 1's x, plus x here. And so we're going to get 7.45177 plus x molar, and then x molar. All the hydroxide is going to come from water, but the hydronium is going to have 2 sources. The 2 sources of hydronium for this will be HCN and water. And so this is the hydronium from HCN, and then X will be the hydronium from water. So now we're going to let the molecules react and create it. But when they react this time, we don't need as much, because all we need is enough to satisfy Kw. And so this is from the previous step here. So Kw is equal to the hydronium ion concentration times the hydroxide ion concentration, which is equal to what? 1.0 times 10 to the negative 14 is a constant. And so we already see this. The hydronium ion concentration increases, then the hydroxide's got to decrease. So X is going to be smaller. And so the maximum value of hydronium from water will be 10 to the minus 7, but what we're going to expect is less. There's going to be less formed because of Le Chatelet's principle and the common ion effect. And so here, well, maybe we need to factor in water, maybe not. So we'll go ahead and do the calculation and see. How much additional hydronium we get from water. And so this is going to equal the hydronium ion concentration at equilibrium, which is 7.45177 plus X times X. This is 7 times 10 to the minus 9. Sorry. I suspect this might fail. This might fail not because of K. K is great for the simplifying assumption. The simplifying assumption might fail because of the initial. We're not starting off with an ocean of hydronium. We're just starting off with a minute quantity. 10 to the minus 9 is pretty minute. But I'm not going to debate that. I'm just going to go ahead and try it. So the SA is going to be that X is smaller than 10 to the minus 9. 10 to the minus 9 is already very small, so I worry, but I'm not going to let that slow me down. I'm just going to go ahead and calculate it. So it's going to be 7.45177 times 10 to the minus 9 times X. And therefore, x, it's such a fast calculation, that's why. It's going to be 1 times 10 to the minus 14. Divided by 7.45. 177 times 10 to the minus 9. And I get an x value of 1.34196. That's plenty of extra digits there, times 10 to the minus 6. Okay, then I try to justify this by calculating the percent change. Percent change is the change, and I could already see the numbers here. The change is 10 to the minus 6. The initial is 10 to the minus 9 times 10 squared. And the percent change is going to be on the order of 10 to the 5th. 100,000%. 100,000% is way too big. And so it fails. Even though it failed twice, it was worth trying. It didn't take too much time. It was worth. So what I'm going to have to do is I'm going to have to use successive approximations or quadratic. I'm going to go ahead with the quadratic. So I'm going to get this into quadratic form. That is x squared plus 7.45177 times 10 to the minus 9. I'm going to write that down here. X minus 1.0 times 10 to the minus 14 is equal to 0. And then if you have a quadratic solver on your calculator, you know, the mid-range budget calculators, I was just looking at the specs, all of them can solve up to third order polynomial, should be cubic. Well, let's put this in. B is 7.45, 177 times 10 to the minus 9. C is negative 1 times 10 to the negative 14. E to the minus 14. 1e to the minus 14. Calculate. And so using the quadratic formula, we get an x equals 9.63435 times 10 to the minus 8. You can see the simplifying assumption is way off. The simplifying assumption gave us an x value of 1.3 times 10 to the minus 6. And here we get 9.6 times 10 to the minus 8. The simplifying assumption is way off because the percent change was way too big. So it was destined to fail. All right, so let's go ahead and calculate the equilibrium concentrations. So the hydronium is going to be this. I'm going to write this this is 10 to the negative 9. So my initial is 10 to the negative 9, and so I'm going to change this to 10 to the negative 9. So if I make the exponential 1 smaller, then I have to make the coefficient 1 bigger. So that way I can just add these up easily. So this is going to equal 7.45177 times 10 to the minus 9 plus 96.3435 times 10 to the minus 9. So what does that equal? So 7.45177 plus 96.3435. And I get 103.79 527 times 10 to the minus 9 molar. So we'll analyze this. The 7.45 came from where? That came from the HCN. And the 96 came from where? That came from water. So which was a more significant contributor to the total hydronium? The total hydronium is 103.7, but which one was more significant, the acid or the water? The water. The water contributed a lot more hydronium than the acid did. And the acid is quite weak.
Did you make a mistake where you meant to write 9.6 times 10 to the negative 8? You wrote 8
I wanted to, I mean, it is 9.6 times 10 to the minus 8. So what I did was I just moved the decimal point 1 over.
Oh, to make it easier to add.
Yeah, to make it easier to add, because if I get the same exponential, then I can just add them straight. And so what I did was I made this 10 to the minus 9. When I made this 10 to the minus 9, 10 to the minus 9 is smaller than 10 to the minus 8. So if you make the exponential smaller, the coefficient has to grow bigger. And so that's why it's 96 here. It's 1 bigger. The reason I did this is, let's call this 100% of the hydronium. Out of 100% of the hydronium, you know, it looks like greater than 90% came from water and less than 10% came from HCN. And so water was a significant contributor to this. And that makes sense because this HCN is so dilute, you know. If the HCN is so dilute, it's almost like pure water. But it's almost like pure water, but don't drink this one because HCN is very lethal. It only takes, I think, on the part per billion level to kill you, which is nothing. But, you know, if this was HCl, no big deal. I would drink it. And I wouldn't worry about dying. But since this is HCN, I won't drink it. And I would worry about dying. But anyway, let's double check the concentrations because I don't know if I did this correctly. I could have made a mistake. And so the hydroxide ion concentration we'll add in here. The hydroxide is going to be just X, which is 9.63435 times 10 to the minus 8 molar. Okay, now we'll double check the equilibrium concentrations by calculating K. And just multiply those two together. And so I have 103, which is still my calculator, times 9.63435 times 10 to the minus 8. And I get 9.99, how many nines is that? 2, 4, 6, 7. 7 nines. 1, 2, 3, 4, 5, 6, 7, and then a 5. Times 10 to the negative 15. And so if I'm going to compare these two numbers here, I want to get it to the same exponential. So this is 10 to the negative 14. So if I got 10 to the negative 14, 10 to the negative 14 is 1 bigger than 10 to the negative 15. And therefore, I have to make this 1 smaller. And so this is going to be 0.79, 1, 2, 3, 4, 5, 6, 7, and then a 5 times 10 to the negative 14. Do they match? So what I'm looking at is 1.0 times 10 to the negative 14 versus this. And so I'd say it's good. If I round this to 2 sig figs, I'm at 1.0 times 10 to the negative 14, so this is good. This is good and bad. This is good for step 2. Step 2 is right in there. Step 2 is looking good. But bad for step 1. Why is this bad for step 1? Because of this, we had about a 10-fold increase in the hydronium in step 2. More than a 10-fold increase in hydronium. But we go back to step 1, and we look at our K value here. Our K value is spot on, just about. Spot on here. This is going to be 6.0 times 10 to the minus 10, which is good. It's spot on here. Essentially the same. But the problem is this. The hydronium changed. This K value was calculated with this hydronium. But how much did the hydronium change? The hydronium changed more than 10-fold. We had a huge change in the hydronium concentration. That's great if you can keep them separate, but can you keep the HCN separate from the water? No, they're in the same beaker. So can I have one hydronium concentration for the HCN and another hydronium concentration for the water? No, I can't. And so this is Le Chatelier's principle. Le Chatelier's principle says, if I increase the hydronium concentration, which direction will this shift? That's going to shift to the left. All right, so that's not a big deal, because what I'm going to do is I'm going to put my new hydronium ion concentration here, and then shift it to the left, and then calculate my new equilibrium concentration. Right. Which will be great for step 1. So what I'm going to do is I'm going to go back and fix step 1. But if I go back and fix step 1, what's going to happen to my step 2 after I fix step 1? Step 1 is going to be screwed up. So I run into this problem where I'm going in circles. Because I get step 2 right, screws up step 1. I go back, fix step 1, screws up step 2. Then I go back to step 2, fix step 2, and it screws up step 1. And then I'm going in circles. Have you ever seen the ants? You know, the ants follow the trail. And there's a leader, and they go in circles until they die. Have you seen that? Well, the same thing is going to happen here. You know, that person who had 3 pages of simplifying assumption, you're going to be here until you die because you're going to be fixing, right? You're going to do step 1, go to step 2, fix step 1, fix step 2. You're going to be doing these circle or calculation and never come to an answer. Or will you? How can we escape this circle of death? Is there a way we can escape it? We don't want to be the ants that go in the circle. We want to be the ant that kind of deviates off the circle and gets out of the circle. How can we do that? Do you know what I'm talking about, the ants? Have you heard that about the ants? No? Yes? Circle of death. This is the ant circle of death here. They're just going in circles until they die. That's what we're going to do. We're going to keep going in circles with this calculation until we die. Unless we can escape. How are we going to escape the circle of death? Average of the two? We're in the Chem 1B circle of death, and there is a way out. You know what the way out is? The way out isn't the quadratic, although it would be nice because the quadratic isn't too bad. We can escape. But we won't be able to escape with the quadratic. We need another method. The method that we've been using is called the stepwise method for solving. Step 1 and then step 2. Let me talk about when we have multiple equilibria. So what we need to do is we need to escape out of the circle of death. And the way we're going to do that is we're going to look at what we do with multiple equilibria. Multiple equilibria. So we had multiple equilibria. We had Ka and Kw. Okay. And those multiple equilibria have a common ion. Okay, so we have two scenarios here. We have multiple equilibria with no common ion. No common species, I should say, because it doesn't have to be an ion. It could be an ion, it could be a molecule, with no common species. / ion. It's called common ion, so I'll throw it in there. Then what we do is we treat them separately. And so we treat them independent of one another, even though they're in the same solution, independently. And yeah, so it'd be separate problems. So rather than step 1, step 2, you have one and then the other, and then you look at it as a whole. Then we have multiple equilibria with common ion or common species. If we have multiple equilibria with common species, common ion, then we have to solve these equilibria simultaneously. So the secret to escaping the Chem 1b circle of death is this. We have to solve these simultaneously to get the same hydronium concentration for both of these at equilibrium. So if we could figure out a way to solve these simultaneously to get the same hydronium that satisfies both these equilibrium at the end, then we're fine. We've escaped the circle of death. You must solve simultaneously in order to get the same equilibrium concentration for the common species. Unfortunately, this is not easy. Since it's not easy, we have some tricks to make it easy. Tricks to make it easy. But sometimes these tricks fail. Tricks to make it easy, but these tricks can fail. The first trick we do is we do stepwise. Stepwise works if successive steps negligibly perturb prior steps. So what I mean by that is that, let's say this step 2 contributed a tiny quantity of hydronium, such that the hydronium really didn't change much in going from step 1 to step 2. Then stepwise is fine. So we used stepwise in 2 previous calculations, and that was with the HCl. For HCl is a special case. HCl is a strong acid, and strong acids are heavily biased towards product. So strong acids, Le Chatelier's principle doesn't work for strong acid. So if I have a strong acid and I add more chloride, it doesn't shift the equilibrium to the left. If I add H+, it doesn't shift it. Their strong acids are, what we say, completely ionized or close enough to completely ionized that they're unperturbed. And so I did a couple of special cases where stepwise did work. Stepwise did work for HCl. It works for HCl because step 1 is not perturbed. You can't perturb a strong acid. Strong acid is going to do what it does. But weak acids can be perturbed. Right? And so in this case, weak acid. Not it. So stepwise worked in the HCl calculations. It didn't change K. K is still very large. The other method we can do is called the combined method. And so we have 3 methodologies: simultaneous. Well, actually, simultaneous should be used for all of them, but simultaneous is too difficult. So we have 2 tricks. The 2 tricks are stepwise, and the other trick is combined. But the problem with combined is it only works for very, very specific circumstances. And it fails for most everything. Fails for most everything. And when I say most everything, it fails for everything in chapters 16 and 17. Wait, what is it? No, 17 and 18. Or actually 16, 17, and 18. Fails for everything in chapters 16 through 18, but for specific scenarios in chapter 19, it works. So whenever we have multiple equilibria, we have to solve them simultaneously. However, simultaneous, the math is too hard, and therefore we do tricks. Unfortunately, the trick of doing stepwise failed here. We can't do combined, it's going to fail here. So the only thing we can do is simultaneous. So let's look at a simultaneous approach to this. When we look at simultaneous approach, then there are two ways that people typically do it. One way is we set up the ice tables and generate a system of equations. Another way of doing this is we go beyond the ice table. We use ice plus we generate additional equations past that. And so we'll do ice plus what we call mass and charge balance. plus system of equations. Or this leads to system of equations. And so, in other words, we can generate some equations based on the ice table, but we can generate even more equations by using a concept of mass balance. Mass balance is simple. Mass balance, you've heard of mass balance before, right? Conservation of mass, conservation of matter, back in chapter 1. And charge balance, you might not have heard of charge balance before, but the charges have to balance. You know, whenever you do equations or whatever else, the charges must balance. And that's charge balance. So, you know, the total positive charge is adding up all the charges on the cations, and the total negative charge is adding up, you know, all the charges on the anions. So we can generate additional equations based on that. And then we solve the system of equations. The book goes through these somewhat.
Do we get to choose which one we want to use?
Yeah.
Or will,
Yeah.
Okay.
Totally. You can choose whichever one you want to use.
And both will work in every circumstance that like this, or?
In theory. In theory. In practice, the math is horrendous. The math, you might do the ice table and system equations, and you go, oh boy, that math is horrendous. And then you go over to mass and charge balance, and you can generate more equations, which makes the math a little bit easier. But it means having to think outside the ice box. Mm-hmm.
Wait, I'm just a little confused about why we're doing this again, as opposed to other ice tables where we didn't.
We're doing this is because we're in this Le Chatelier's perturbation loop, where each time we solve the ice table, it screws up the previous one. So when I solve for step 2 here, let me label this. Here, this is step 1. Step 1, okay, looks good. Everything looks good, right? And then I move to step 2. When I move to step 2, it looks good. You know, I even said it looks good, right? But what I have to realize is both of these equilibria are in the exact same beaker, and I can't have two separate hydronium ion concentrations in the same beaker. So in the same beaker, is it possible to measure a pH over here that's different than a pH over here when it's at equilibrium? You can't have two pHs in the same cup. You know, somebody gives you, I'm going to give you some pH 7 water, and it turns out, hey, wait, this is not pH 7, this is pH 10, you know. You're trying, well, it's pH 10 over here and pH 7 over there. No, the pH is going to be the same in both. So this is an impossible situation. You can't have two different pHs in the same beaker. You can't have two different hydroniums in the same beaker. And so we got to fix it. We got to fix it. The situation, though, for the previous problems with HCl is it didn't change anything. It went to completion, and that was it. And if you add more, it's not going to shift it because strong acids aren't shifted by Le Chatelier's principle. Strong acids and strong bases. It's a one-way. This is why I called it a one-way. There's a very specific reason why I called it one-way. I don't know if you wrote that in your notes. I call it one-way because one-way means don't bother with Le Chatelier's. One way means we aren't going to have to worry about it perturbing.
So the amount of hydronium would be the same in both concentrations.
Yeah, we need the amount of hydronium to be equal in both of these
Right.
simultaneously.
Which is like a variable, and then for this equation.
Right.
Doesn't sound too terrible.
It doesn't sound too terrible, so let's set it up here. So I'm going to set it up over here. I'm not going to do mass and charge balance here. In class. What I'm going to do, the mass and charge balance, I'm just going to post this. I have it worked out. I'll post it on Canvas or something. You can see how you can do it there. All right, again, I'm going to start with HCN here, plus H2O, liquid. This is going to give me hydronium plus cyanide. And so we have Ka for HCN here. And then initial, I'm going to do it like this. I'm going to write it here. I'm going to assume that we start off with no hydrolysis of HCN. That is 1 times 10 to the minus 7 molar. And so I'll just write this as initial here. And then the hydronium is going to be like this. There's going to be some hydronium in there initially. Where did the hydronium come from? The hydronium is going to come from water. This is going to be from water. And then I'm going to reset this so that no cyanide is there. And so this is kind of a Le Chatelier's type problem, here, where we reset it. But we aren't going to produce as much. So we're going to lose minus X of our original initial, and then we'll gain plus X molar here and plus X molar here. And so this is going to be the HCN initial minus X molar. And then over here we'll just have the H3O plus from the water plus the X. X is going to be the hydronium that's going to be generated from the HCN. And then we're going to have X molar cyanide here. Okay. Now, how should we deal with water? Water is, how much hydronium am I going to have here initially from the water? You would think it'd be 10 to the minus 7, but it's not because there's HCN present. And so we're going to have hydronium here and hydroxide here. And since we have hydronium present from the HCN, how much hydronium is present from the HCN? So I'm going to call that the hydronium that's going to be generated from the HCN. Well, you know how much hydronium is generated from the HCN? We call that X. Right. And so over here, the HCN is going to generate additional hydronium, which is X. And that's what I'm going to have here. The hydronium from the HCN is X, whatever we generate. I don't know what X is, however much we generate, because of the common ion effect. The common ion effect is here. But I'm going to reset the water. So initially there's no hydrolysis of water. And so this is 0 molar here. And then I'm going to allow this to hydrolyze. But I don't want to use X. So I start off with the waters not colliding. And then I'm going to, instead of calling it X, I'm going to call it Y, because I already used X here. And this is X here. So I don't want any confusion. So what I'm going to do is the change here, I'm going to get additional hydronium, which we'll call Y molar here. And this is going to be plus Y molar here. And so the hydronium generated from water is Y. Well, that's this. This is the hydronium that was generated from water. So I'm going to call that Y up here. So this is Y here. And so at equilibrium, this is what I'm going to have. I'm going to have the hydronium that's generated from the HCN plus Y. And this is just going to be Y molar over here. Okay, and then I'm going to make this a little bit easier, because the hydronium generated from water is Y, and the hydronium generated from HCN is X. So at equilibrium, I'm going to have Y plus X here. And down here, the hydronium generated from HCN is X, and this is going to be X plus Y. So do you see that the hydronium will be equal simultaneously, because Y plus X is equal to X plus Y. And so we have equal hydronium. And so this is what I mean by simultaneous. These two equilibria will simultaneously have exactly the same amount of hydronium, and therefore it's not going to perturb things. Do you see that? So it's just a matter of solving. Rather than solving for X like we always do, we're going to solve for X plus Y. Or X and Y. We need to solve for X and Y. So what are the equations that we're going to generate? So if we have two unknowns, we need how many equations in the system of equations? 2. So one equation is going to be this. We'll just write this as the Ka equation here. The Ka equation is, I'm going to put Y plus X times X divided by the HCN initial minus X. Okay, that's equation 1. Equation 2 is going to be Kw. Kw is going to be the hydronium times the hydroxide. So what we're going to have here is X plus Y times Y. And then you go simple. Simple. 2 equations, 2 unknowns. Isn't it simple? And then the problem is this. It's not simple. Because when you look at it, let's solve for X. Let's solve one of these equations for X. If we solve this equation for X, what do I have? I have XY and Y squared. I guess I could solve it for X then. X is going to equal something over here. But or I try to solve this equation for X. If I solve this equation, this is a quadratic. How do I solve a quadratic for X? Well, I can use a quadratic equation, right? Or I solve this for Y, but if I solve it for Y, it's YX. And so what happens is this. Even though this looks simple, this is very difficult. This is very difficult because we can't solve it easily without using tricks. And so we're going to use some of the standard tricks to solve this. And then we have to think a little bit out of the box. You know, thinking a little bit out of the box, it's easier to solve this for X plus Y than it is, you know, an X or a Y. So it becomes more and more difficult. And so this set of simultaneous equations is difficult to solve. But it can be done. Use the tricks in the book, like the simplifying assumption, this kind of stuff, et cetera, et cetera. Yeah. Then you may be able to solve it. To try to simplify the math, I think it's easier to solve this using mass and charge balance. This is easier because the algebra is a lot easier. And you don't have to use tricks to solve it. And so I think this is easier. But you need to generate, we generate like 5 different equations for this. Something. Or more, at least more than 2 equations. Since you're going to spend a lot of time solving the math, and this class is not an algebra class. You could stop here for full credit. That is, you have to recognize it's simultaneous. Or you can continue for bonus credit. If I were to put something like this on the test. You know, you just have to recognize that you're in a death loop. That's all. And how do you get out of the death loop? You get out of the death loop by solving it simultaneously.
So this will usually happen with a weak acid or base, right?
Yeah, right.
But hydrocyanic acid is a weak acid.
Hydrocyanic acid is a weak acid. It's a very weak acid. Hydrocyanic acid is 10 to the minus 10. Let's so we could place it on our acid chart here. Hydrocyanic acid is 6 times 10 to the minus 10, so it's slightly stronger than ammonium, but weaker than boric acid. So it's weak.
So anything 10 to the minus 3 or lower, we consider weak acid?
Actually, anything lower than 10 to the minus 2 is the biggest of the strong acids, or 1. Actually, 1 is hydronium. But you see the strongest, so the weak acid is 10 to the minus 2. So anything 10 to the minus 2 and lower, or 10 to the minus 1. 10 to the minus 1 still considered weak. Strong acids are going to have 10 to the positive, 10 to the positive big.
Gotcha.
So is this expected for every single weak acid you measure?
No, not at all. Not at all. The problem is the concentration. So I told you we could do stepwise if it doesn't perturb. If I made this, rather than making this 10 to the minus 7 molar, if I made this 0.1 molar HCN, which is like 1,000,000 times more concentrated, if I made this 0.1 molar, then step 2 does not perturb it. Step 2 is going to add a little bit of hydronium, but the amount of hydronium it adds is like a drop in the ocean. Barely anything. So it doesn't perturb it. And so if I made that concentration bigger, and so in other words, if you want to know when this scenario happens, when you get into the death loop is when you have a weak acid at low concentration, then you're in death loop. Or if you have a weak base at very low concentration, then you're going to be in the death loop.
Are we going to be typically asked to solve this at higher concentrations so we don't end up in this death spiral?
No, if you do solve this at a higher concentration, then you can solve it stepwise. It works stepwise. Stepwise is not correct. Stepwise, it's the same thing. It's the same thing. All gases we should solve using the van der Waals equation, but the van der Waals equation is a pain. The math is a pain, right? If you solve the van der Waals equation for V, do you know you have to use the method of successive approximations? Because it's not easy. I think it's third order or fourth order polynomial. Is it third? All right. Well, you could use a calculator then too. But the van der Waals equation is not easy. So what do? We use the ideal gas law. The ideal gas law is a heck of a lot easier, but does it work all the time? No, it doesn't work all the time. When it fails, what do we have to do? When it fails, we fall back on the van der Waals equation, and we just stick it out. For the equilibrium law, we should use activities, but we don't have the activities, and so what we're going to use we're just going to assume the activities are close to the concentrations and pressures. But if that fails, then we have to use activities. And so it's the same thing here. For multiple equilibria, we should be using the simultaneous method for all of them, but the simultaneous method is a pain. Do you see the math there? Try this at home. There's lots of things you don't want to try at home because they're dangerous. Well, this might be dangerous too, because you might get so frustrated that you might end up committing suicide or something like that. Try it at home and then see that you don't want to do this ever. But sometimes you have to. So it might be wise to look. You don't have to in Chem 1B because you can still get full credit. But I'll post a key how to do this if you're interested in it, using both methods on Canvas. So what we do is we just use the ideal gas law. We just use K with concentrations, pressures. We just do this always stepwise. We always do this stepwise because hopefully it works, and therefore we don't have to deal with this simultaneous stuff. But when it doesn't work, it clearly doesn't work here, then we have to just state that we're in this death loop and we're stuck. We have to use the simultaneous method. So you could set up the simultaneous method like this and you get full credit, but you don't actually have to solve it, because when you could take this home and try to solve it at home, it's going to be very difficult, you'll find out. And it'll take you time. However, people who've done it once or twice, they know how to do it, and then the second time you do it, third time, you can be very fast. And so some people have solved this simultaneously very fast.
to prove that you will be in a depth loop for full credit, or can you just look at the concentration and?
No, the proof is just saying this. Step 2 perturbs step 1. That would be the extent of your proof, significantly. If you redo this calculation with 0.1 molar, you'd see that there's so little hydronium produced in step 2 that it doesn't change it. Step 1, really.
I mean, I bet I've asked this before, but if it's at a larger concentration, do you still want us to do step 2? If it's, you could assume that the amount of hydronium the water would add would be very negligible.
You would do step 2 if I asked you for the inventory, but if I asked you for pH, then no, you don't have to do step 2. Oftentimes you don't have to do step 2 if you can just see that you have so much hydronium that water's not going to impact it. We'll do an example of that where you can see.
So if it's asking you for what the molarity is of the hydronium, you want us to do step 2 regardless, right?
No. If it's asking you for everything in solution, then you do step 2. Everything in solution, there'd be some hydroxide in there. So in order to figure out how much hydroxide you have, you'd have to do step 2. But if you're only interested in pH, and step 2 you assume is going to be negligible, then you could just stop at step 1. Save yourself time. But the thing is, how do you know when? And so what we're going to have to do is, I've been telling you, what's the most hydronium you're going to get from step 2? The most. You should 10 to the negative 7, and due to the common ion effect, you typically get a lot less than 10 to the negative 7. And so if 10 to the negative 7 or less doesn't have any impact on your initial, then you worry. When I looked at this previous problem, I knew I had to do step 2, because how much hydronium did I have? After step 1, I had 10 to the negative 9 molar hydronium. Then I'm thinking, well, I got to do step 2. I have to do step 2 because if you have 10 to the negative 9, then hydronium could be significant in water. However, if this were 10 to the negative 3, and I'm looking at something less than 10 to the negative 7, like 10 to the negative 8, that's 5 orders of magnitude smaller. That's 5 decimal points further. Probably isn't going to make any impact, you know? And so you look at this and then you determine, you know, will 10 to the minus 7 or less make an impact? If it won't make an impact, then skip step 2.
That's kind of what I was asking.
Yeah.
If it's a larger polarity for the weak acid, and you know the water wouldn't have much of an impact.
Right. Then that's correct, yeah. All right, we were talking about acids. I just want to finish up talking about bases. And looking at the conjugate relationship. So ammonia is a weak base, and it has a Kb. The Kb is 1.8 times 10 to the minus 5. The first thing is B stands for base plus water, or base hydrolysis. And so this Kb is for a very specific equation. What is this Kb equation? The Kb equation is ammonia plus water makes what? Yeah, ammonium and hydroxide. So when we think about bases, we're looking at hydroxide producers or hydroxide contributors. So base solution, hydroxide producers, acid solution, hydronium producers. So this is their Kb. Our Kb is going to equal the ammonium concentration times the hydroxide ion concentration divided by the ammonia concentration. And water has an activity of 1. And this is what gives us the ratio of 1.8 times 10 to the minus 5 here. The next thing is, where did this 1.8 times 10 to the minus 5 come from? Because when I look at that table is a Ka table. Are we missing a Kb table? And what you find out is there's really no Kb table because there's a conjugate relationship. And the conjugate relationship is this. I'll just state it. That the Ka for the conjugate acid, which is ammonium, times the Kb for ammonia is equal to Kw. So the Kb values are calculated. Kb for ammonia is equal to Kw divided by Ka for ammonium. And so all I do is go to my acid chart and look up the Ka for ammonium and then plug it into this equation, and I'll get 1.8 times 10 to the minus 5. And so the Kb values, they don't need another table. We can easily calculate the Kb values. And that's where this Kb came from. All right, I'll stop here since I'm out of time. Talk about this. We'll continue chapter 17 next week. Oh, do you want your Scantron back? If you want your Scantron back from yesterday, I'll give it to you. If not, I'll give it to you next week. Ashley, June, Sahari. Christian, Shane, Jonathan, oh, sorry, Christian, here, Kayla, Jacob, Isaac,
I have to go to my room.
Sandy,
There is fine.
Antonio, Alan, Gianni, Tess, Eric, Katie,
You certainly do.
Kenji, Katie,
Wait, no, you can.
Dylan, Caesar, Gavin, Nicole.
Do you have boxers?
No, not today, but
We're all-
on Monday. Kiana,
I did that one.
the free response I'll have graded sometime over the weekend. Let me just send that to you, Canvas.
Will you post the actual exam?
Yeah, I'll post the key to the exam, probably today sometime.
So far, damn.
Okay. It's 12 and 16?
Yeah.
Okay. Okay, we have to leave here in a second, but Nicole, right. All right, so I fixed it. It should show up on the Canvas when I input it.